Greetings, gentle readers. Today is July 19, 2025. And today, from a study with Ross Finlayson, here is Logos 2000, 21st Century Foundations. What's been arrived at is that foundations is the study of the grounds of reason and then all of theory. So it's rather ambitious and grandiose. Yet that's for what it serves is kind of the logic of being and the technical sense. It's very compelling to researchers and students in foundations to have a foundations, and that then it provides for these theories of reason. So you can find these sorts notions, deliberations, and their contemplation since antiquity, since prehistory, and many or most authoritative works intend to detail aspects of it and provide grounds for its cognition and its interpretation, and to relay these ideas of foundations. So here, what's arrived at that's any way different from that is that there is a sort of a principle of inverse instead of a principle of contradiction. And then the principle of sufficient reason has furthermore a principle of sufficient and thorough reason. And then for the logic, there's basically a reliance on the absence of mathematical and logical paradoxes and the reasons why it's kind of extraordinary up front for this ubiquitous ordinals to make for a universe of logical and mathematical objects. After this principle of inverse and principle of sufficient and thorough reason for these inductive and deductive courses, and it refused to be trapped in the inductive impasses when furthermore or overall there's this deductive and the analytical bridges which may so result, and as well that the analytical bridges of deductive analysis make for so that the inductive courses can find themselves to be kind of fulfilled in what they intend to entail as this bright line of successive reasoning and as after the empirical. So there's a principle of inversion instead of contradiction, and then there's a principle of sufficient and thorough reason and the fulfillment of it. It's kind of ascribed to them. The principle of sufficient reason and the principle of contradiction are the most basic fundamental aspects usually of given a reason. Why then that's in line with all the canon and dogma and the doctrine of our candidates for foundations since antiquity, and as well since the great golden ages have come and gone again and over again, which make for so that the attachment of these principles can then make for this axiomless natural deduction to so arrive at for a fundamental question of metaphysics that there is all the question words to be answered, and then they have answers, so that thusly there can be sort of a universalist theory, is same from the nothingness of the theory here in the logical setting and the grounds again of the reason. So that is not always found in all accounts, but can definitely be seen in many particular of the Aristotelian, the Kantian, and otherwise that being as for the great Greek and German schools of the ideal and analytical traditions, for idealism and the analytical tradition. So that's piling upon or allowing to convey the authority of what otherwise provides the authority to any other account of this kind of thing. Those same ones with this furthermore more full or fuller overall dialectic. Then into the mathematical, it gets to that there's the continuity and infinity are rather primary, and then there's deconstructive accounts of algebra and arithmetic and analysis after geometry and number theory for topology and function theory, and that there are three models, three different definitions of continuous domains, because the complete ordered field, as the usual linear curriculum would intend to import, has that's sufficient for many purposes, particularly for delta epsilonics, And then after set theories, point set topologies, and definition of models of Hardy's real numbers as of elements of geometry and elements of arithmetic, and the axiomatization of least upper bound and 1.0 properties to provide the completion, fulfillment after limits, the completions of the complete ordered field. Field reals here. There are also line reals, which are kind of this simple, more prototypical line drawing, this act of seeing that an integer continuum would also provide for a linear continuum, if only between 0 and 1. And it's provided for apologetics to explain after modern mathematics and set theory that it doesn't contradict cardinality, or rather the results of uncountability, when it's possible to instead show that this thing can exist. And primarily because it falls out of the arguments for uncountability uncontradicted. And then as with regards to the analytical bridge to there being a countable continuous domain, it's as simply so that this function is not Cartesian. So it's just a simple sort of result that proves there exists a function that is not Cartesian in the usual sense of axiomatic set theories, descriptive set theories accounts otherwise of all these things then for as what axiomatic set theory and descriptive set theory as have been used to formalize all of mathematics that was formalized in the 20th century is still so maintained. Then the ubiquitous ordinals provide kind of off the top of that how then that the larger aspects of there being a continuous domain, or as for uncountability, can so remain uncontradicted. And then there's this third sort of continuous domain, this signal reals. So at least three definitions of continuity or continuous domains instead of just one. And that there's analytical treatments of them as the real valued systems. So it's called, instead of real numbers, if that's only going to be the members of the complete ordered field, as for the real valued, that then there's at least three models of continuous domains. And mathematics has them. And as mathematical Platonists, we can kind of say they exist instead of saying that they're invented or axiomatized to exist by us mere mortals and finite creatures. This is, of course, quite a usual school since thousands of years ago that these sorts of objects make for themselves to exist, and that strong mathematical Platonism doesn't necessarily entail all of what Platonism is intended to entail for ideals and idealism, but it does make for that they're ideal mathematical objects, or a perfect circle in a straight line. That then the strong mathematical Platonism is that these objects exist. Sometimes maybe phrased these days as Aristotelian realism, because after this other side of the analytic tradition, the logicist positivism, it was instead changed from the old idea that truths are discovered, that axiomatics provides the truths. And so even for something like Euclid's treatment of the elements of geometry, or a treatment of the elements of geometry, and here there's an axiomless geometry that makes, after simple logical considerations, a spiral space-filling curve as this line drawing, and the emanation from the origin of order mathematically, meaning this strict ordering of things, that thusly Euclid's elements then are seen to so follow. And so it's not so necessary to maintain that attachment while still providing for somebody like Derrida or Husserl this overall sort of connection to this world of geometrical objects, which are so much the pure mathematics since antiquity and even today. It's a heno-theory of sorts, meaning one theory of all these objects and all their structures has to fulfill being all these different theories' roles that are fundamental theories in mathematics, like the arithmetic, the algebra, and the analysis of the geometry and the number theory. For the topology and function theory, as is for our analysis about them in the operator calculus, the idea being that geometry and number theory play this alternating role, of which comes first, and then that they neither can be without the other, and then both together they make this more fulfilling, that like these three continuous domains each have this property of completeness, meaning there aren't any gaps, there aren't any leaps, they're perfect, as Leibnitz might have put them, or as after Hilbert's axiomatization, that is so that this least upper bound property is given. And often people don't realize that that's an extra axiom after ZFC to make the reals exist, that it is so. And then the measure 1.0 is also the other axiom, given to that reals exist, that it is so. That these line reals happen to actually evince this themselves, so that way it can help provide that there can be geometry and mathematical objects on their own, and that they can be discovered in this manner. So with those being each complete, then it's said to be that they're more replete together. And this is considered as of the most sort of required thing for mathematics to have, because otherwise then it can be considered and shown how expansion comprehension can arrive at contradictions and otherwise break theories that would purport to deny these things. So here what we've been talking about, and adding to the theory, adding to the usual school of the theory, without yet taking away much anything, is the principle of inversion after or before the principle of contradiction, so that we're outside of just the land of the purely tertium non datar. There's no third ground. Every question's got a yes or no answer, and such notions as arrive at the paradoxes of material implication, or fallacies, one might say. There's a principle of sufficient and thorough reason, and furthermore, principle of sufficient and thorough and fulfilling reason. And so this just helps go to show that not merely is it necessary that it suffices for an account to be given of an inductive account, but it has to live with every other account, a recount story, account being a structured premise and all its entailments in terms of its monotonicity, one hopes, of the modality, of the relevance for modality and relevance logic, of the surrounds, the entire mathematics. If it's going to be a foundations, it can't have anything that's mathematical object that does not live in it. So the candidate for foundations have grown from being things like geometry and later to the analytic about when things are not continuous, then how to handle things like the infinite, if at all, and then how to help provide these completions for these limits mathematical of like the infinite limit, or first the inductive limit, then the infinite limit, and then as finally sort of the continuum limit, as what can be seen to so arrive at these stronger sorts of results, when after very, very simple examples, it can be shown that merely inductive accounts of the existence of a limit are not complete. And then these are the kinds of things that, while taking away some of the axioms of the theory, still arriving at more of the requirements and desiderata of the theory to make for then that this not so easy to be meddled with or tipped over, and for something like Chrysippus's moods to counter Plotinus's modes or lack thereof. Aristotle won't be made a fool, and we can find in him these greater sorts of accounts than soi-disant Aristotelians may have made from partial and half accounts. And so this is kind of considered necessary for any foundations, that it has most of this background to arrive at something that can be more complete than what we have today as the premier theories of the philosophy of the logic and reason. The logic itself, then, as to be quite truth valued, and then for things like don't know, don't care, or otherwise the correct sort of assignment things which result in the truth tables for the propositional calculus or for the predicate calculus, and then for the eventuality of everything being in the first order as regards to schemas and strata and ramifications of types as according to higher order terms and these kinds of things like hereditarily ordinarily definable, or the cumulative hierarchy of set theory and transfinite set theory. As with regards to ordinals and cardinals, two different things for counting and numbering irrespectively. That it so follows that this helps avoid the kind of the shambles of the class set distinction that is followed in all these different accounts trying to like add on and pile on top of this, while not yet having been fully reflective of the assumptions that went into all the objects that there are of them, and so making these sorts rehashings that are kind of, if not doomed to fail, because sometimes they can be defined as just invincibly ignorant themselves for being, say, not self-contradictory, that yet in a wider world of this fuller dialectic, that they are, it is not doomed to fail either, this bigger, fuller account, which can consider those as merely irrelevancies, yet it still it attains to the same things that these things are purported to reach to, like completeness and universals, and there being a universe at all, for example, and the resolution of mathematical paradoxes, which is all kind of done up front. So this is a little bit more thoroughly and fully addressed, like in these podcasts or my thousands and thousands of essays written onto the internet. But here, it's kind of a nice recapitulation that, so far then what we're looking at is a mathematics as its foundation that's, compatible and includes set theory, which is used today for all the formalization in the world, as for things like category and theories of types or other modes or representations, languages of the equi-interpretability of what may so arrive from proof theory and model theory. That here, this structuralist account after a deconstructivist account and a restructuralist account of a model theory then is very much so compatible with then that all the usual results of the linear curriculum just sit there the same, while anything that ends up being analytical, say, over the course of completions, and as for the infinitary, is changed from having sorts of uniqueness results or inexistence results to distinctness results, or further openings, perestroikas, catastrophes, all those all being the same word in this mathematical sense, of then for these three continuous domains. So there are three continuous domains instead of just one. And that it tends to reflect that for the laws of large numbers, so if those are geometries, continuous domains, then numbers, the integers, have their infinities. So this is kind of discussed as natural continuities and natural infinities. So there's kind of at least three of those too. Fragments, extensions, and a standard right down the middle, that we've kind of picked to use a standard one, but when really it was just fragments and extensions that would kind of so arrive at it. We, meaning it was given to us because this initiative of modern mathematics as a candidate foundations was underway hundreds of years before today. And so the idea then that these three continuous domains have kind of three different kinds of infinities, not greater and lesser, except just kind of growing and shrinking or expanding and receding, that for things like Skolem and Mirimanoff, those being names of people who showed that infinity is greater or lesser than itself in these various kinds of ideas, has that there's no standard model of integers for number theory. Many conjectures inside the integers that trail off at the end for the infinite are independent standard number theory. There are other concerns, other fields that intend to tell for like various conjectures of Goldbach, or whether there's a prime or not at infinity for number theorists, have that those are open. So many of these sorts of otherwise interpretations which can be arrived at given kind of a half account or an inductive account can be re-examined. And so that's just to say then for these three continuous domains, there's at least these three laws of large numbers for these three kinds of infinities. And then there's, for Cantor space, the sequence of all the zeros and ones, in the language and the words of algebra, of a formal language, zeros and ones, infinitely many of them. This is called Cantor space, after Georg Cantor. Also written as 2 to the omega, for 2 being this ordinal 0, 1, or the language thereof, is this in a kind of a shorthand notation, and the omega being this ordinary infinity, little omega, whereas big omega is given to the absolute infinity, And then here I would just frame it as like the infinity of the natural numbers is like n, or blackboard n, and then something like n plus 1 or n plus variously about that, or n minus as these various means to write a natural infinity, say. Whereas n is just the usual set of a set, an inductive set, an ordinary inductive set of natural integers. Then these other ones are like so. So this Cantor space then has at least three kinds of Cantor space. There's the sparse Cantor spaces, which is that which is usually given, because after the establishment of uncountability and that the real numbers are uncountable, and so that most of them are not rational or algebraic, as rationals and algebraic numbers are countable, those being fractions and roots of polynomials, roots with integer coefficients, and some systems of continued fractions, that the algebraic numbers and rational numbers are countable. And so most all of the numbers in this Cantor space, as given originally, are not as of the rational or algebraic. They would as represent transcendental numbers, given that each of these sequences of zeros and ones can represent exactly one number between 0 and 1 real number of the non-real part between two integers, 0 and 1. So there's this Cantor space in the idea that, well, most of the numbers are not rational. So we might contrast this with Pythagoras and the Pythagoreans for whom all numbers were rational. And if any were not, then it's like only that one, like pi, is not rational, or root 2 is not rational. Before they went finding these other algebraic numbers as regards to them being rational or irrational and algebraic. And these transcendental numbers are most of the numbers. Yet in another account of the real numbers, there are almost none. So this helps to show that for this Cantor space, then there's at least two ideas of how many of these numbers are what. And one is almost all, and one is almost none. So there's another idea of the Cantor space, and this is for the line reals has a countable continuous domain as simply a fraction of the limits of n over d, numerator over denominator, for integers n and d, natural integers, as n goes to d, that it ranges over that d goes to infinity. So this is the simplest way to model a function that has these properties. Constant monotone, strictly increasing. That being one property, meaning it is increasing strictly, meaning it never decreases or goes flat. It is increasing strictly, and it's constant and monotone, meaning it never changes whether it's going up or down. And so it's just constant, monotone, strictly increasing. These four properties usually as this always the same terms as mathematics uses everywhere. Give for that, then this function ranges between 0 and 1 as the natural numbers. The domain ranges from 0 to infinity. And that it's accountable is given by that it's related to the natural numbers. Thus, the 1-to-1 and onto, a bijection exists, a function. And then that it's a continuous domain is given by extent, it ranges between 0 and 1, inclusive. Density, it has the property that in every neighborhood of any point, there are infinitely other points in the same neighborhood, according to the usual, any of a usual number of topologies, especially when they happen to be a continuous topology, which is shown initial and final topology. Not necessarily the usual open topology that topology courses in the standard linear curriculum give as a candidate or putative topology for usual theorems about the rationals and irrationals in the open and closed in topology, the theory. That then the extent and density are so comprised, and then completeness is we discuss no gaps or leaps left over in these. This is a property that the rationals don't have, and the irrationals don't have, and also the transcendentals don't have in any given region. They're just having the same property of having extent and density, but not completeness. And then measure is so ascribed. So this is the measure 1.0. And then these line reals just kind of have, without having that they do have these sigma-algebras that provide all the tools necessary for them to live with other theories of measure and make for the theorems of calculus, that it is sort of a length assignment. So that extent and density are given by the properties of this original function, and completeness is given as sort of trivial, that the least upper bound property holds because it's next, and so that's satisfied. And then the measure 1.0 is given for a length assignment, and then a variety of sigma-algebras sort of naturally fall out of it, making for measure theory, that sigma-algebras are necessary to be so defined, to so equip this putative, countable, cardinally continuous domain with being properties of being a continuous domain, that mathematics otherwise doesn't really have this kind of usual idea in the course. It's got continuous functions, not continuous domains. So this was kind of discussed in those 3 podcasts about the continuous media, the continuous functions, and the continuous manifolds a bit earlier last year. It's been a few months since I made a podcast, but I'm quite content with the fact that I most thoroughly agree with their content. So this second Cantor space then is a square Cantor space of this function, and so it's countable left to right, and it's also countable up and down. And furthermore, it's like, well, yeah, you can take off the initial segment of each thing, and it's kind of 2 copies of what results, because it's an infinite balanced binary tree, and just kind of written in a that a depth first and breadth first traversal are the same thing. And so when that's written, it's just a sequence of the zeros and ones, that then this property, the square Cantor space, is kind of fun, because then it sits in the middle. So here we might say that something like, well, half the numbers are rational and half the numbers are irrational. And then, but it might also be says like, well, half the numbers are algebraic and half the numbers aren't algebraic. So that kind of is why then it's like, well, then I guess we better have a model where there's at least 3 laws of large numbers, that most of number theory is independent when it comes to the infinitary reasoning, yet it can still be arrived at the consistency and the multiplicities of these things with regards to indeterminate forms and their resolution, and inconsistent multiplicities in the resolution. So that's just, and then this third kind of Cantor space, Cantor space would be, as for these signal reals, or otherwise a representation for these 3 different continuous domains. One imagines they kind of have 3 different representations, because the signals are all the possible signals that could so reconstruct it. So there's kind of more of those cardinally than there are of the usual cardinal of the continuums, real numbers in ordinary standard set theories account, after defining LUB in measure 1.0 to give model real numbers. And then relating that back to, by the section between 0 and 1, the values of this Cantor space, because also the power set result is so reflected in Cantor space as those also being all the different representations of subsets of the natural numbers. So that Cantor space is involved in a variety of things, as relating both subsets of the natural numbers just by an indicator at each offset, whether or not the nth element is in the set. And then also as for a real number being all these infinitely many Bernoulli trials, or the nth inverse power of 2, its flag indicating whether or not that's part of the sum of the series, so comprised that any of these real numbers, which has any of these representations like so, is that Cantor space is in the middle as something like that its elements are members of all the possible subsets of the integers, or here for something like and that's usually assigned to the sparse Cantor space, and then this other Cantor space, and then this other one for the signal Cantor space, again for these field reals, line reals, and signal reals, or rather line reals first, and field reals and signal reals. Then this square Cantor space would kind of be first, and then sparse Cantor space, as for the ordinary infinity, is what it comes to entail at, and Cartesian functions, so that any functions can be a composition of any other function, where this equivalency function, the natural unity equivalency function, n over d, is simply not a Cartesian function. It can't be reordered. that then these signal reals so follow as making for then these three kinds of Cantor spaces. So 3 continuous domains, 3 types of infinity, and 3 Cantor spaces, and then getting into probability theory and statistics is for more limit theorems, because now the various ideas of, and including stuff like that there's multiple things involved in probability and statistics about the Bayes rule and classical expectations, and after the definition of a sample space and events and the probability distributions as functions and random variables and really truly random variables, and the statistical validity or the statistical hypotheses of the scientific methods statistical hypothesis, that there's for something like the Bayesian, then there's also like the Jeffreys and the Knightian for both conditional probabilities and then uncertainties as well. So they're getting involved with things that, and besides things like this natural unit equivalency function has, well, you know what? You notice that it is a PDF and it is a CDF? And that then it's of a distribution of like the natural integers, all infinitely many of them at uniform random. That's not standard. And indeed, someone was like, well, that's impossible, because if I were to assume that something could define a counting argument that way, it would decimate any counting argument. It would reduce it beyond its irreducibility, say. But that it exists is always already given us, like, well, ever since Zeno's arguments 2,500 years ago, we already knew that there were classical accounts of the superclassical which cannot exist, yet they do. And so having it so, then for probability theory, that something like one of the central fundamental uniqueness results in probability theory is that a distribution is defined by exactly one PDF of function, exactly one CDF of function, and exactly one MGF of function. And the idea then that there exists a non-standard distribution, like the natural integers at uniform random, and they don't have a unique distribution among these various non-standard functions, is quite available then to make that a distinctness result for this case. So after the infinitary reasoning, given that you've already equipped the mathematics with these necessary and needful things to have a consistent and thorough mathematics, is what otherwise would be lacking, as what otherwise when necessarily introduced to show for their properties that they're natural for something like time or that they hold, would contradict other aspects that are so built that cannot accommodate them flexibly at all. This makes for so that, and then in probability theory, there's, for the limit theorems then, something like, for the central limit theorem, this great central crux of all this Gaussian in the probability theory, and after Poisson and the Gaussian, is then there's like uniformization limit theorems. There's analysis of variance, analysis of covariance, and so there's the convolutive setting and things like polar limit theorems, where it's like, does this distribution have a mean? It's like, no, this distribution naturally buckets into two different quantities. It does not have a mean, yet it does have some other elementary statistics that so reflect that when you sample these two things, you're not going to get an average value, even if they add up to an average value over time, or for a given small number of samples. That in the large numbers, it really is so that. This is then is for the it would be called non-standard in any standard setting, but here it's considered superstandard and extraordinary, vis-a-vis our usual standard and ordinary setting. For then the standardization and normalization of probability theory and all the great things that go for the transformation of functions that make for transformation of distributions. Has that then this special sort of function then finds itself kind of central and primary, and it's kind of good that it wasn't really included in the standard linear curriculum and all the usual account, because now it just kind of it stands out so much that it's like, well, that makes sense, because by kind of trying to figure out then how things relate to it at least will have to also relate in related rates and all these kinds of things for like model relativism and this kind of thing throughout to maintain it be so correctly, to keep the bookkeeping to have like a greater sort of account of continuum mechanics than what there was before. So this way, a lot of what's been going on, and for me, this has been 30 years ago. I said, hey, it's definitely got to exist like that. And then I took the long road to try and figure out how that could be when all the modern mathematics, which we weren't really given as introduced in our secondary and university curriculums for real analysis and stuff like that, which were just kind of given, the fundamental theorems of calculus from the properties of arithmetic real numbers, and those were just kind of given as primary, in the theory. That then learning all about that then is really greatly interesting, because then for the infinity of these things and trying to figure out for the continuity and discontinuity, or the continuous and the discrete, has that then these continuous domains is from sort of geometries, and then these discrete domains is from number theories, really do live in back and forth for each other. So I'm happiest about that, because and I definitely would not give it up for anything. If anyone when one were to come along tomorrow and say, I've got this theory and it's exactly like was just stated here over the past half hour or so, I would say, well, I kind of most certainly agree, and so that is and it's something that it also has that is mathematically justified, and furthermore that then kind of the entire enterprise is justified from having the theory overall with this principle of inversion and sufficient and thorough reason, and being able to look past the inductive faults and inductive impasses with these analytical bridges that then for a logic that kind of holds it up and together, and for the Mengen-Layer set theory with like ubiquitous ordinals in this for cardinals and ordinals together, and all together, that it's considered an improvement and necessary. And so I'm pretty much delighted about that. So, and that covers then these ideas of these natural continuities and natural infinities, of these continuous media manifolds and functions, into the infinitary reasoning of combinatorics and this and that. So one thing I discovered about this back in 2003 or so, I picked up a factor probability theory. And then I was looking at counter space, and I made some deductions about like, well, what would be the contents of the rows and columns? And then I was looking at it, and I said, well, one of these sequences of zeros and ones, how many of them are absolutely normal, meaning any subsequences is likely to appear as any other, and that over time all of the subsequences appear with the same frequency. So that's called star distributed or absolutely normal, kind of depending on whether you ask Donald Knuth or not about it. And so then the idea was that then there's Borel spaces, and that's kind of like after the algebra of words, and then there's combinatorics, which is kind of like just counting arguments on these sequences from the left-hand side, from the beginning. And so one arrives at almost all of them are so, and one arrives at almost none of them are so. And they're both quite standard accounts. And so this fits in with lately like the Ramsey numbers and all this kinds of stuff. Or I guess it was Erdős who said it was like the giant monster of independence or contradiction if you don't allow for independence. Contradiction can be so directly demonstrated if they're not just like outside, extra, and super what we already have. That this Borel versus combinatorics then became a Borel vis-a-vis combinatorics, and then right in the middle is this square Cantor space, and then for things like is it 0 or 1, or is it 1/2, and then these doubling spaces and halving spaces and doubling measures and halving measures show up a lot, and not just in the later current accounts of like the non-standard or the quasi-invariant and these kinds of things. If one thing I didn't mention yet, well, I guess we haven't really gotten to physics yet, but one thing I didn't mention was, I'll mention in a moment, that these ideas of, well, when is it we've done the analysis and now we have to like divide it by 2 or multiply it to have it work. And so it's like, well, it's just a fact of after going to the inductive limit, then the infinite limit, then the continuum limit, sometimes it either doubles or halves in the one-dimensional case. So this is something that made me happy, because then I also discovered like another formula for factorial, 10 times 9 times 8 times 7 times 6, if 10 were infinity, You know, this makes me quite delighted, because now I feel like I have a theory that this will stand up for itself, and it's both defensible and resistant to meddling. It's true, and it helps bring a lot of these issues in the ambiguities and paradoxes of logic, and helps fix them. So that's always good. What I was going to mention about physics was then that for physics we have kind of a sum of histories, and then this a conservation law. And so much of the idea was like, well, instead of just a principle of contradiction, there's a principle of inverse. And then instead of a principle of sufficient reason merely, there's a principle of sufficient and thorough reason. So the conservation law is furthermore continuity laws, because the energy is quantity, so represented is also energy and entelechy. So like the contents, the energia, and the entelechy, the connections, and so it's a continuous manifold. So that kind of equips physics with some more requirements to make it so that there's always going to be a way to describe that is defined, that is necessary to have these continuum laws hold up, which they do in almost all cases, except for where there's when there's shear and the transverse and stuff, and layers, that's its own sort of treatment of models of flow and models of flux and these kinds of things. But it would still so hold for the energy alone case with also this entelechy. Then the entropy, either way and both ways, can kind of be rehabilitated a little bit. So then it's a sum of histories theory, and then it's a sum of potentials. That it's overall then for this fuller account, it's the potentialistic theory and the sum of potentials that is as so or more eventually relevant, if not immediately tractable. I mean, if more difficult to consider and set up, then it's still at least kind of later more fully thorough and better and truer, more true. That this sum of histories and sum of potentials then have for least action and least gradient, then that as well as like nothing is really inclined in its tendency to do anything, but there's always sort of a propensity from all the outside world that it does, that equilibrium is always reaching equilibrium and this kind of thing. Makes for then that this principle of inversion and principle of sufficient and thorough reason kind of arrive at this axiomless natural deduction, that there's an axiomless geometry, an axiomless physics. Well, it's still just kind of these same principles, because then it's as for the strong mathematical Platonism and strong logicist positivism, or the idealist and the analytical traditions together forever. Then there's this one to have it for this mathematical universe hypothesis. It basically follows a clock hypothesis, because to describe that time exists as a quantity, it's kind of like, well, a linear continuum exists, and then any means of like walking along that line or drawing the line then results that it's in time, and then space so follows is just kind of what the infinities and infinitesimals of the linear continuum could hold in itself as a hologram. So in modern theories of physics, sometimes you'll find description dimensionally as that all the resources kind of fit in a lower dimension. Sometimes it's in higher dimensions. In fact, most of the time. Because people will say is like, well, I'm modeling 3 dimensions of space and 1 dimension of time, instead of like 3 dimensions of space and maybe just a ray of time. And so there it's already kind of grown then because with time being anything otherwise than unidirectional. Then it's like, well, make for Kaluza-Klein and add 1 more dimension, so we got some way to make perspective on anything and just kind of look around the corners. Well, then add it up for that is getting up in a Klebsch-Gordon or something, or any other model. Just keep adding dimensions. Keep adding dimensions whenever you find that you've hit a brick wall or a nonlinearity or a highly unlinear, highly nonlinear rotational setting or anything like that, and just add more dimensions. That quickly gets cumbersome, and the problem is whenever it loses itself from like true Euclidean analyticity, everything being kind of on a continuous manifold, then and these accounts are often built up in the complex numbers, where also these things are claimed, sometimes rather than proven, to maintain these properties of conformal mapping and continuous transformations, besides even having given up the affine and the geometrical, because torsions get introduced and introduce their own particular singular settings, and there's multiplicity theories. That then the, how one might say, dimensional analysis is kind of overflown, and then figuring out how it can be less is what's called the hologrammatic setting. And that's basically the idea is like, well, we live on a line, and then all this stuff, and in detail is like, yes, we can see it out in projection in 3 dimensions, and it's great, and it's got everything in it, but instant by instant, we're still on the same line of time. And so how does that correspond with like theories of relativity in the 4th dimension? It's like it goes great. Any one of those is that setups is just its own little thought experiment. Whereas they still then, well, how can they, I can see how they can fit in more dimensions, because I can always just add more dimensions and say it's one or the other. How does it fit in less? It's like, well, it's kind of figured out it can't really fit in less than this 3 plus 1/2, 3 for space and 1/2 for time, because the linear continuum's kind of got, you know, infinitesimals and infinities in it, and it's kind of a great circle, whereas and then the time is just like the simplest thing that keeps it going. And so if that could be so for y, then that's so, then that is kind of a reason why. Then for foundations, at least, this clock hypothesis in a universal time sort of precedes this mathematical universe hypothesis, which is that these same objects are eventually like this heno-theory, and all the panoplies and all the infinite diversity and infinite combinations, to quote a fictional character, all these things still exist. Well, it's all still this constancy and consistency, completeness, and constancy and concreteness, that the theory, thusly, of a mathematical universe is not just that the universe's physical laws obey mathematics in their models, but that it's also a projection of the existence of some great perfect continuum of what that may be as an objectively sort of available to reason and logic thing that exists for us to discover, not so much to invent. And we can make analytical treatments with their formalisms, with particular ruleal and regular formal systems and descriptions in the languages and formal methods to have for axiomatics. And that's indeed one of the great strengths of our axiomatic tradition in all such matters of the analytic tradition and right thinking, reasonable things that can be relayed. Yet it's in these foundations where it's like you're going to need universals and infinity and continuity someday, and all of reason over thousands of years has already figured out ways you can't do it. So you better come up with something that you can, and at least using these usual standard linear ways, as people agree that they don't know together, has that then, again, this is just an idea that for a strong mathematical universe hypothesis, that it can kind of exist. And that it's the result of whether it's just a perfect creation or whether it's discovered as we must remain agnostic of that in a sense, because both the Big Bang and the steady state theories of origins of the universe fit the data, and they always will, and under any conditions, because it can always be so arbitrarily contrived whether the universe has been eternal and always existed, or whether it's just a brief flash in the pan and after some finite time. So either way, it's good. And in fact, both ways, it's better. And that over time, it appears that every 20 years since the Big Bang hypothesis was kind of stood up by inflationary cosmology, the universe got billions of years older. Because the more they look, they're like, well, we put the next higher generation telescope online, and we should be able to add a zero and walk away prosperous. And it's like, oh, yeah, well, what happened is like, well, we didn't, but now the universe, to fit in our formulas, is a billion years older. It's like, okay. So every time they look, the universe gets bigger. And then conversely, every time they look at atomic particles, they get smaller. And these are just called the running particles. According to the particle data group of the National Institute of Standards and Technology, code data, who defines these things at least at this national level of what the measured constants are for the interchange and things like the journals that for the running constants and these kinds of things. It's that it's part of this one world, one universe type of approach with the mathematical universe hypothesis and a clock hypothesis to so proceed for a hologrammatic setting. So this way, foundations can be, at least on the technical side, giving and equipping mostly mathematics with all the stuff that it needs, because it needs to provide that to physics and statistics and probability theory too. For science, because science and probability theory are very much very close together. And then as for with regards to like objectivity and interobjectivity and subjectivity and intersubjectivity, it's relayed that there's mental and object senses, like for the numerological, the object sense, word sense, time sense, number sense, sense of the continuum, to complement our sensuous senses of the phenomenological. As with regards to historically over time, for like the Epicureans and Sophists are like the only thing I'll possibly accept as an account that is on the face of its so intersubjective. And so then the idea of this intersubjectivity and interobjectivity is stood up. It's like, hey, if we're going to be Aristotelian realists, because this is very much what would be called a realist position, not a nominalist position or a fictionalist position or otherwise of the pick them up and put them down variety of theories. This is that there's a good theory at all, and then it has to be all the good theories that go together. True. So that's then to just kind of trail out for this brief recapitulation of what we're looking at here in Logos 2000, is that that's a great theory, and I think it's the current candidate for foundations of mathematics and after logic and reason, and then for physics and the mathematics of probability and statistics and science. It's and science too. So it leaves out a lot of details. It's like the famous old cartoon, and these two white-coated scientists are standing at this giant chalkboard full of all these equations. And then he's writing so all these equations, and then he just arrives at his constant. But right before that, he's written, he's like, here a miracle occurs. And the one scientist who says to the one who's author, he's like, maybe you could fill out a little bit more of this detail right here. So I'm not saying that there's anything necessarily not intersubjectively relayable, but I will definitely describe that this is just the theory we can attain to vis-a-vis the one we have. But the only way that something else could attain to and have it is for it to be this way, because it's kind of self-describing in this sense. So the cartoon where the guy's like, after all this detail, and for some people that would be the totally inscrutable part. That's like, it's all Greek to me, meaning it's like, well, it's either in Greek or it's like formulas and symbolary and letters of an alphabet for their condensed abstract symbolic meaning that is inscrutable. That then the idea then as well, it's like for the scientist or the formalist, it's like the bit at the end is like, well, maybe almost everywhere or close enough, and it's like, yeah, could you complete this a little bit more right there, So to get from like, well, we at least have a theory of mathematics, and it makes number theory a lot of conjectures open again. But it does have three continuous domains, so they're not fighting each other all the time and eventually going to contradict each other in any kind of formalism in the theory. And then to arrive, like how can physics kind of arise from this and that kind of thing? Gets into like a tetrad of quantities and this kind of thing. With the idea that there is one at all, and it's very natural. It's the natural science is the idea. Well, I didn't know how long that was going to take. I thought maybe in 5 minutes I would just kind of recapitulate and say, principle of sufficient thorough reason, principle of inverse, rehabilitate all this kind of stuff. But that makes me happy because it covered quite a bit of ground. So let's take a look at some of these books here. They're just kind of in the stacks, and we'll be looking at them. The Logic of Chance, Ven's The Logic of Chance. You ever hear about Venn? He's like, all Venn diagrams are kind of from Venn. Combinatorial Optimization by Papadimitriou and Stiglitz. And it's got stuff like magic squares, Dirichlet cells, a recognition problem, Cook's theorem, integer knapsack, partitions, combinatorics. Combinatorics and graph theory often going hand in hand. An introduction to information theory, symbols, signals, and noise. So imagine, see, this is Dover reprint, and this is Well, and this is Well. Dover really reprints a lot of great works in mathematics and physics. Here then, let's see what this is. A Survey of Numerical Methods for PDEs, edited by Gladwell and Waite, from Oxford Science Publications. So, briefly, elliptic equations, interpret this as the steady state equation for heat conduction. These kinds of things. A practical patch test. Hundreds and hundreds of pages. Integral equations. Oh, let's see. Now, having numerical methods for integral equations has that most of the work and publications have gone into differential equations, but integral equations, as discussed here in the integral different integral, are just as deserving, and maybe even more so. The idea of alternating directions arises naturally from consideration of the classical block or line Jacobi method. See Isaacson and Keller, 1966, for a clear exposition of the classical iterative methods applied to Poisson's equation on a rectangle. It is the possible improved convergence rate of the ADI method over the successive overlaxation technique which gives the method its importance. This is guaranteed for certain model problems. Alternating direction implicit methods, splitting methods. And so that may be a little stronger and more structural and more organized than usual analysis of variations and the perturbative or Monte Carlo methods. Alternating. And here that's reflected in things like the notion of the alternating and resonating dimensional alternator and dimensional resonator is the idea. So, a course in elasticity. B.M. Friges de Vuibeke. Springer Verlag, Applied Mathematical Sciences 29. So this is elasticity. And it's about kinematics, fundamentals, and elasticity almost invariably from the treatments I've seen at it always start with continuous, the continuity equations or the continuity conditions, and so here's kinematics of continuous media, and the elastic constitutive law. So here that's reflected in the usual phrasing of things in terms of the oscillating and restitutive, and the attenuating and dissipative, the reconstitutive and the constitutive equations and these kinds of things. And as was mentioned, that's like the energy and the entelechy. 3 classical applications of theory, each one of the 3 topics. Saint-Venant has got some great stuff going on. Theory of prismatic beams. These are just like that. If you take a snapshot of something that's vibrating back and forth, it will according to like the snapshot, or rather the strobe of it at any given rate, you'll see particular artifacts that come out of it. But those are just kind of the prismatic in this sense. And the bending of plates. And then he gets into quite a thorough and continued treatment. Conditions for the univalence of G only need to be satisfied for one member of each of the equivalence classes of irreducible circuits. For these we choose the directrices of the cavities, so we have this integral because the sum of integrals, because this integral equals that. With the constitutive equations, this becomes a reduced form, and an integral of a dot product, and an integral of a difference, minus these 2 coefficient prefixed integrals in terms of x squared minus y squared dx plus 2xy dy. So the terms, like as if it were like x minus y squared, negative x minus y squared. X minus x squared minus 1, x squared plus minus 1. Another one of the usual things here. Oh, here's this fuzzy neural networks approaches in engineering. So before we're looking at something about the fuzzy and neural network approaches, and this is from the Lotfiedsaude himself. He's written a foreword to Tsoukalos and Erg's book. So this is like all the neural nets are like after this quite a ways. So maybe we already looked at this a little bit, but I'll put it back later. Well, that's a few of these stack here, and this is just a usual course here to find some things. Oh, this was some of this American Mathematical Monthly. It did have some mentions of stuff in the non-standard probability from the 70s, just like, yeah, it's on the radar or whatever. And this is one of these stronger type theory books, isomorphism types. Roberto de Cosmos, From Lambda Calculus to Information Retrieval and Language Design. He's got some great developments of productions in type theory and types that provide higher level types. Well, gentle readers, I hope you've had a great day, and happy 4th of July, Independence Day in the USA, and these kinds of things. And yeah, this kind of idea of how is Logos 2000 gonna finish out with like about 52 videos, and to have reached kind of a philosophical point. If descriptive differential dynamics kind of was to find the original analysis of the identity dimension and to start making for the original analysis for the stop derivative and some of these other ideas about the infinitely many higher orders of motion. And then the moment in motion was almost entirely inspired by the infinitely many higher orders of motion to arrive at world's turn and be a pretty thorough account of stuff like Zeno's swath and the hypercube distance. These being mathematical objects of some perceived import in terms of any system of change, and to be quite thoroughly analytical and super classical. Then Logos 2000 is helped to kind of combine the philosophical pieces, and then as well has touched on a couple points there where there were things mathematical in them, but mostly it's been the philosophy here. So I shall probably proceed in that way, and then just going through stacks of books and just finding relations in any of these, usually postgraduate research level textbooks, or reference manuals, or industry field manuals, or works of reference, the stacks. Thus, good day, gentle readers. Logos 2000. Geometry is motion.